see my screen and hear me? Hi, students. Can you see me? Can you see my screen and hear me?
Yes.
Can.
All right, that's great. So, mark your attendance. So you're done with that. And we're going to start today's lesson by continuing where we left off, which is on the extreme value theorem. So today we're going to cover the applications 2 for our week 11 material. So as you know, this is pretty much the last week of new material, I hope. So we will be starting on week 12 material today, which is on mean value theorem as well as the optimization. Subsequently, today, once we finish week 11 stuff, right, you can hand up your last homework for week 11 next Wednesday. So today we finish week 11 material. Next Wednesday, you hand up week 11 homework. So that will be your last homework. Because week 14 is actually your examination. So next week is week 13. So you hand out the last homework. So therefore, week 14 is your examination. So in this case, you need not hand up week 12 homework. Okay, I'll make an announcement posting in the week 12 channel. So don't have to hand up week 12 homework. Okay, reason being it's a bit too close to the examination, and the grader, he has his own what do you call that, examination as well. Okay, so I just want to cut everything by week 13. Okay, so week 11 will be your last homework to hand up, which is next Wednesday. So we're going to continue and recap on our extreme value theorem. So as I mentioned before, extreme value theorem is a bit like common sense or very intuitive, very logical. So it says here that if your function is continuous and it is on a closed interval, and we discussed about, to some extent, what is the concept of closed and open interval. So closed interval, in a nutshell, right, it really just means that your bracket, the interval bracket, must be square brackets. Okay, must be square brackets. You cannot have round brackets. So the concept of the closed and open interval here is actually, when it's closed, right, it includes the well-defined limit at the two limits here. Okay, it includes the well-defined value at the two limits here. So therefore, if an interval is open, which means that if you see any one of the brackets being round, then it's considered an open interval. Reason being, what is open? Open to interpretation. Because if you look at, for example, this example here, whereby if your a is equals to 1, but your this round bracket cannot include the function, cannot include the limit value at 1. So therefore, in this case, you can actually arbitrarily choose the left limit to be at 1.001, 1.00001, and so forth. So therefore, there is no definite value that you can choose for this open so-called limit. So hence, right, this type of interval is considered open. Okay, so you can, have a mnemonic for this, which is open to interpretation. So hence, some of you may be wondering, what is the concept of bounded and unbounded here? So bounded and unbounded really means, right, whether one of your limits contain infinities. as any one of the limit contain infinities, then it will be considered unbounded. All right. So therefore, going back to the EVT here, extreme value theorem here, obviously you got to have this closed interval whereby your limit is finite and also well defined. Then you can always have a maximum and a minimum value. Okay, so that's the extreme value theorem. And I mentioned before that even if your function is a horizontal line, you still can get the maximum and minimum. It's just that maximum equals to minimum equals to that constant. Okay, so this is also true. This extreme value theorem is also true if your function fx is just equals to a constant. Okay, so if everywhere is constant, right, then clearly in this case you just get the mean equals to max equals to c. Okay, so regardless, it does not violate the extreme value theorem in this case. So therefore, this is an example whereby we went through, right? And you can see that although this interval from from 0 to 2 here is considered closed, this part is closed, right? But however, this part is open. So during this first portion, right, of course, this interval is from 0 to 2 is a combination or is a union of two separate intervals. 1 to, I don't know what value is this, but I think this is 0 to 1, 0 to 1, and this is 1 to 2. Okay, so you can see this part, right, is actually open interval. So when this part is open interval, right, then we are not able to so-called definitely state the maximum at x equals to 1. Okay, because you can see that this approaches 3, right? So this is arbitrary and open to interpretation already. Okay, so hence there is actually no clear maximum. Okay, so of course this violates the conditions for the EVT here, right? Because your what do you call that? First of all, your function is not continuous. Secondly, this part, right, there is an open interval. Okay. So today we're going to continue Fermat's theorem. I think we left off at Fermat's theorem here. Okay. So Fermat's theorem basically just states that, well, if you have f prime c, so you just look at this 0.6 here, right? This 0.6 here. So if you have f prime c equal to 0 or does not exist, so these two conditions, right? Either one of these two conditions, right? That means you can actually find a critical point. So this critical number is just the value of x or the value of your independent variable for which your function achieves a critical value. Okay, so critical, as I have mentioned, right? Critical so-called value is just a fancy way of saying maximum, minimum. Okay, local max or local min. So therefore, at this critical point, right, also known as a stationary point, although critical point comprises of two types. One is stationary, the other one is not a stationary point, but can be a critical point, can be an extremer. Okay, so critical in this case, right, is more general. Okay, it's more general. So what is stationary point? As the name suggests, stationary point just means that when your f prime is equivalent to 0. Okay, so when the gradient is horizontal or the slope is so-called 0, you have a horizontal gradient or tangent, then you have what we call a stationary point. So the concept here is, imagine you are walking across this maximum or minimum point, right? You will appear stationary to someone who is looking at you from the horizontal, okay, in the horizontal direction. So therefore, it is known as stationary point. Okay, so besides stationary point, another type of critical point, right, whereby the f prime does not exist is known as such points whereby you have a coops or sometimes also known as a kink. Okay, so therefore at this point, right, you can clearly see that it is not differentiable, and we say that f prime c in this case, right, do not exist. So where's your value of c? So value of c is actually here, right here, right, at c equal at x. So this f prime c do not exist. So if you recall, what is the definition of f prime to exist? Well, the left limit must be equivalent to the right limit, must be equivalent to the function value at that point. okay? Or else this thing do not exist, right? So hence, we take a step back all the way to, I think it's week 2 or something, right? Whereby you look at limits, okay? So in a nutshell, left hand, right hand limits must be equivalent, okay? So hence this f prime c, right, do not exist. And we can just eyeball this and we know that this gradient is actually a negative gradient, this gradient is positive gradient. So how can the two gradients be equivalent? Okay, so hence f prime is clearly not existent. So this is the whole idea here. So when we want to check for critical points, right, or in fact local minimum, local maximums, right, we just have to find out where are the x values or where are the c values that f prime could possibly be 0 or f prime could possibly does not exist. Okay, so that's the whole idea here. So we can conclude that if c has a local extremum at c, that means f prime c must be equals to 0 or undefined. Okay, as mentioned before. So therefore you can see here, right? So in the same illustration that I've drawn just now, so the slope when it's or the tangent when it's horizontal, right? Then you have the stationary point. Okay. So these are some examples of the consequence of Fermat's theorem. As you can see here, we have a critical point at C here. So this is clearly a stationary point. So this is clearly a stationary point. And this is clearly a critical point whereby your f prime does not exist. So this stationary point will be f prime equals to 0. So this is a critical point which is non-stationary, but however, your f prime does not exist. Okay, so the same thing goes with this guy, right? So this is also a critical point. So f prime do not exist. And you can see that this guy, so this guy is actually having this stationary point, but this is a point of inflection. Okay, point of inflection. So you can see this critical point, right, is not representing a local extrema. Okay, but it is a critical point. Why is that so? Because as I mentioned just now, critical points include stationary points. Okay, of course, this drawing is not very clear here, right? Let me draw more, because the point of inflection is having a 0 gradient right at the inflection point itself. Okay, so you can see this point, right, is exactly having a flat gradient here. Okay, so in this case, we have our stationary point, which is f prime equals to 0. So hence, a stationary point is also a critical point, but clearly this guy is not an extremum. Okay, so this brings me to the point that it is not always true that if you have either f prime equals to 0 or do not exist, right, you definitely must have a you definitely must have an extremum. Okay, so hello, let me mute. Okay, come and hear some feedback here. Hold on, huh? What's happening? Hold on, let me try to mute all here. Okay, let me continue. So as I was saying, right, Fermat's theorem states that if you have a critical point, then f prime equals to 0 or f prime do not exist. So therefore, if you want to find the local maximum or the local minimum, or generally just maximum or minimum points, then you have to look for f prime 0, f prime equals to 0 or f prime do not exist. But that does not mean that when you get f prime equals to 0, you are definitely going to get a local max or local min. Okay, right? So understand the logic here. So therefore, we look for it, okay? But we still, after that, have to inspect whether it's an extremum or whether it's just a point of inflection. Okay, so that will come in more examples later on. So therefore, this is f prime equals to 0. And you can see here that actually f prime do not exist here because this part, right, is actually a vertical. Okay, so the point of inflection, right, is actually looking like that. So it goes vertical, and then subsequently at the point of inflection, it turns back. So therefore, you can see the gradient here is actually infinity. Okay, so f prime do not exist. All right. Okay. Let me just get the chat box back. So this is what I just mentioned, right? The converse of Fermat's theorem is actually false in general, right? Even though when you have f prime equals to 0, there might not be a maximum or minimum at C, yeah? Okay, so precisely demonstrated by this inflection point here. Okay, for example, given by y equals to x cubed quite easily. So same thing here, right? So exercise caution when you apply Fermat's theorem. Okay, so we have to do further checks. Later on, I'll tell you how to do the check. Okay, using a first derivative test or a second derivative test. So let's look at this example. Supposed to find the critical numbers of this function here, right? So hence what we do is just differentiate. Okay, no big deal. We just want to differentiate and we look at the x values for which f prime equals to 0 or do not exist. So after we differentiate, okay, of course this is you need to use your product rule here. As you can see, function of x multiplied by function of x, but you should be quite proficient in it by now. So therefore, after we differentiate, then after that we make the common denominator, right? So hence you get this simplified expression here, which is looking like a fraction. Okay, so we can actually inspect at which points, right, does this f prime equals to 0. So quite clearly, you just set this f prime equals to 0. So multiply by the denominator throughout, you will get 12 minus 8x equals to 0. So 12 minus 8x equals to 0, you solve for x, you get x equals to 3 over 2. Okay, so this is a candidate for your critical point. This is a candidate for your critical point. Okay, however, we still do not know how to classify what kind of critical point it is. It can be a max, can be a mean, and it also can be inflection points, etc. Okay, so now this, actually, this is wrong. So this should be f prime. Okay, this should be f prime. So f prime does not exist when x equals to 0, which is pretty clear because if you look at this denominator, when x equals to 0, the denominator equals to 0. So therefore, you got division by 0. So hence, this f prime function cannot exist. So hence, 0 and 3 over 2 are the critical numbers of f of x. Questions? So we're just using the first derivative, f prime, to assist us in finding the critical numbers. Looks good. So move on. So how do we locate the absolute extrema? So this absolute here, right, will mean that you have a closed interval. Okay, you have a closed interval. So as mentioned here, right, the EVT says here that a function, a continuous function in a closed interval has definitely a maximum value and a minimum value. Okay, so as we discussed just now, right? So practically you must look for points at which, so let me write here. So if you have a closed interval, so let's say my function is like that, and this is included. So this is A, and this is B. Okay, hold on. Let me just give maybe one of the possible critical points. Maybe something like that. Okay, so hence, now you're going to look for two things. In the interior of the interval, you have to look for, one, f prime x equals to 0 and f prime x do not exist. Do not exist. This will be inside AB. Okay, now this inside AB is important. Why? The reason is because, right, when you solve for f prime equals to 0 or f prime do not exist, the x value, the critical number, can be outside AB. If it's outside AB, then you practically ignore. Okay, because the question, right, states that I want to locate the extrema in the interval AB, right? In this closed interval AB. So therefore, if your critical number, you have to check the critical number. If that number is outside of this interval AB, it does not belong to the candidate for an extremer in this interval. Okay, so we have a demonstration later, right? So this is number one. Then secondly, right, you also have to look for the n values. Look for F, FA and FB. Okay, so basically you have to compare across the board. So therefore, find the critical number, check whether it is inside AB. If it is, then put it as one of the candidate, and then also compare with the extreme values, okay, or the function value at the extreme limits, right? So then finally compare. Then compare. Okay, so of course, the lowest value in this case will be your minimum, then the highest value will be your maximum. Okay, so those are known as the extremer or absolute extremer when your function is defined with a closed interval. Okay, so let's look at some examples to demonstrate these two steps in a while. So you can see the demonstration here is that what happens, right, when you actually do not have a closed interval. Okay, so firstly, on this top left diagram here, so this is actually your y equals to x cubed. So when you have y equals to x cubed, you do not have a closed interval. Okay, so you do not have a closed interval. So clearly in this case, do you have an extremer? No. No maximum slash minimum, as we can see. Okay, so this minus infinity to infinity, right? So which means that actually this graph goes on to infinity, positive infinity. This guy goes to negative infinity. So clearly there is no global or no absolute min max. Okay, so I think that's pretty clear. So what about this guy? So this guy is actually interval over open unbounded, right? Interval is unbounded and open. So you can clearly see that this guy, right, has no minimum. Okay, no absolute or no global minimum. It does have a maximum though. Okay, so what about this guy? So this guy, right, you can see that the interval is also minus infinity to infinity. So therefore, right, is there a global maximum and minimum? Well, the answer is yes. Okay, so therefore you do have a maximum here. This is a global maximum, and this is your global minimum. Okay, but however, once I want you to contrast this, right, where you have no closed interval with closed interval. Now, when you have a closed interval, you are definitely going to have a min or max. Okay, so let's see this. So you can see that this guy, right, is going to be, let's look at E first. So hence, right, you can see that there is an absolute or global minimum. So this is your minimum. And you also have a global maximum or absolute maximum. Okay, so you might observe that actually the minimum occurs at f prime equals to 0. But the maximum is actually an endpoint. Okay, so therefore that's what I'm trying to say when I say that just now for point 1, right, you have to find f prime, the critical numbers, right, for which your f prime equals to 0 or do not exist. Put it down as one of the function values. Okay, calculate the function value, for example, f at 2 at this point. Okay, f of 2 at this point. Then you need to compare with the n values. So altogether, you actually have 3 values to compare here. Okay, so let me draw a table. So for example, E, right, when I want to find the extremum, this is what I'll do. So this is my x value. Then this is my f value. Okay, so for example, if I solve for f prime equals to 0, I will get x equals to 2. So therefore, I need to calculate what is my function value at 2. So I put a 0 here. Okay, because I can clearly see from here that f equals to 0. Okay, I don't really care what's the function here. So you can see that, what about at the endpoints? So at the endpoints, the left end here will be 1. So x equals to 1. Okay, let me use a different color. So at 1, right, this f value is giving me 1. Okay, then at 4, this f value is giving me 4. I compare. So these three function values I must compare. So by inspection, clearly, this is going to be my minimum. And this guy is going to be my maximum. Okay, so of course, in agreement with our graphs here. Is that all right? Okay, so whenever you have a closed interval, you will have to do a comparison using a table in this form. Okay, you might not need to use the table, but you have to, compare all the so-called candidates for those extremes. All right. So, well, we come back to this part here. So this part, right, actually there is no maximum. Okay, there is no maximum. But although the interval is closed, hold on. So although the interval is closed here, right, but because it's discontinuous, so when you have discontinuity, right, of course, your Fermat's theorem cannot apply. Okay? So then this part is also because we have this open interval, and this is unbounded here. Okay? So your so-called this guy is an open interval, so the interval is actually including 0, open at 2. So therefore, in this case, right, you cannot apply your so-called extreme value theorem as well. Okay? So practically, if you look at all the different cases here, right, I just want to illustrate that when you have a closed bounded interval with a continuous function, you are definitely going to get some mean or some max. Okay? Some mean and some max. So that's your extreme value theorem. Okay? So this is actually the 3 steps that I've illustrated just now, right? It's just that maybe the order is different, but the idea is the same. Okay? Evaluate f at the endpoints. After that, find all the critical points of f, and then subsequently just do a comparison. Okay? Just do a comparison. Exactly. So Kevin asked, right, what happens if you have max and min points? That's what you need to do. That's why you need to do this comparison. Okay? So clearly, if you have multiple maximum and minimum, for example, if your graph is maybe like that, so clearly you are going to get all these as critical points. So you're going to have 4 critical points. But when you compare the function value, you are really going to see that this f, right, is going to be your max. You see that? Okay, this guy is going to be your max. So which means in your table, right, you're going to have 1, 2, 3, 4. Then after that, with the 2 endpoints. So you're going to compare how many values? 6 values. Did I answer your question, Kevin? Okay, so no problem. Because if let's say you have sine or cosine function, sinusoidal function in general, right? Basically, what you're going to get is you're going to get multiple so-called basically periodic values of C or periodic values of your critical number for which value is always returning you the same. Okay, so which actually means that you got so-called infinite critical points. Okay, if of course your your interval is unbounded. Okay, of course, if your interval is closed and bounded, right, then you got to count how many points are there, okay, in the interval, right? Because your critical numbers are actually appearing in a periodic fashion, okay, in a periodic fashion. So let's take a look at this example and to make things concrete. So we have to find the absolute maximum and absolute minimum values over the specific interval. So this interval is closed, okay, and state where those values occur. So we're going to check 2 things first. Going to check 2 things first. In fact, the solution actually did not say, which is bad. Okay, so let me just step 0. Okay, hold on. Let me just put it here. Step 0, and this is important. So pre-check lah. Let me call this pre-check. Okay, so you're supposed to find absolute maximum and absolute minimum values over this specific interval and state where those values occur. So because you realize that this interval is closed, since interval is closed, and check out this function. This function is just a polynomial function. So therefore, this function is defined for all R, continuous in R. So therefore, f of x is continuous for all R, then there must be some, or rather, a maximum and minimum. Okay, a well-defined maximum and minimum, right, in the interval. Okay, according to IVT EVT, by extreme value theorem. Okay, so therefore you are definitely going to get some finite values of your min max, right? So hence you do step 1. So therefore step 1, right, it's possible that you interchange step 1 and step 2, doesn't matter. So therefore let's evaluate f at the endpoints first. Okay, so we clearly can observe that f, right, at 1 is equivalent to 0, f at 3 is equivalent to -2. Let me see if they draw a table. Yeah. Okay, so you can see 0 and 3. So 0 and -2 respectively. Okay, so they got these two values from step 1. Okay, then subsequently step 2. So you solve for f prime do not exist or equivalent to 0. Okay, so you're going to solve for both. So therefore, f prime is actually just a linear function. So you set it equals to 0, you can calculate x very easily. So your x is actually 3/2. Then make sure you have to check, is this 3/2 inside the interval? This is important. By the way, this is a very common trick question that I will give. Meaning to say, I will ask you to find f prime, then you find the critical number, then most of the students will not check whether this critical number is inside the interval. So they put that as a candidate. Okay, then of course you might get the wrong answer because the maximum at which this critical number occurs is actually outside this interval. So if by right, it shouldn't be considered in the first place. Okay, so therefore this check is important. I'll put it very clearly here. You must always check. Okay, so hence this 3/2 is 1.5, right? It's definitely inside 1 to 3. So this is indeed a candidate. Okay, this is indeed a candidate. So hence, right, we have to get the function value at 3/2. Okay, so get this function value. So you get the function value is equivalent to 1/4. So then that's all. So because f prime do not exist is not possible. Okay, because f prime is always defined for all R, right? So therefore, there is no f prime do not exist. So hence, we can see that we have 3 values here. Okay, 3 values here. So therefore, just a simple comparison will give us -2 here, right, is our absolute minimum. 1/4 here is our absolute minimum. All right. So I hope this demonstrates the idea about EVT and how that can be used to find our min and max, right, in our closed interval. Questions? Good. Moving on. So key concepts here, you can read them yourself. So right here, right, maybe let me illustrate an example of what I mentioned just now. Okay, you must check whether the critical number is inside your interval or not. Okay, so a simple example could be, let me just give you one more example to make this thing really clear. So let's say we have f of x is equivalent to, okay, let me give a cubic function. Let's say x cubed plus maybe 2x squared plus 3, let's say. Okay, so therefore, now I ask you to find the extremum, right, in this closed interval. Okay, in this closed interval. So I'm going to decide this closed interval in a while, okay, because I don't know where's the critical point here. So therefore, I can do a check on the critical point first. Okay, but of course, before that, right, pre-check. So pre-check, f is continuous. F is continuous in R, in the interval, right, in R, and interval is closed. Okay, interval is closed. interval is closed. Okay, so therefore, so we have a mean and max by EBT. Okay, in this interval. So now, step 1. So we do f prime first. So f prime x, right, is equivalent to 3x squared plus 4x. Okay, then I solve f prime x equal to 0. So I want to get the critical point. Okay, so because this can always exist, so this is well defined in R. Okay, so f prime exists for all R. Okay, so you cannot have do not exist. So we just check f prime equals to 0. So in this case, quite clearly, right, you can get 3, okay, let me factorize out x. So you get 3x plus 4 multiplied by x equivalent to 0. So you can see you get two critical values, x equals to 0, x equals to 0, comma, x equal to minus 4/3. So now you have to check whether these two values are inside my interval. So let's say I purposely go and put this interval. Let's say I put this interval as, let's say, 1, 3. Oops, sorry. Let me put it as maybe -2, -1. Okay, -2, -1. So I ask you to find absolute mean max in this interval. Okay, so this is my question. So now, right, you check, is 0 inside here? It's not. So therefore, right, you have to omit this value already. Okay, so hence this one, let me put in a different color. Ignore this number since outside -2, -1. You see that? Is that right? Okay, so ignore this x equals to 0. Do not calculate the f value at x equals to 0. Okay, that means do not put it as one of your candidates for comparison. You only do this one. Only do this one. So this one, right, is inside -2, -1. So calculate the function value. So f at -4/3. Okay, whatever this is, I don't care. Is that right? Okay, so that's the first part. Then second part, of course, you calculate what is your, let me put a different color here. So second part, find f at -2, f at -1. Okay, of course, this trivial, we don't waste time here. So now, thirdly, compare. Okay, so how we compare? Draw a table. So x, f of x. So hence we get what? We get 0, -4/3. Maybe use the same color. So this is my -4/3. Then the f value is f at -4/3. Then the other two values at the extremes. -2, f at -2, -1, f at -1. Okay, then from the three values, right, which one is higher and which one is the highest, which one is the smallest, right? Decide your mean max. Okay, questions? So compare to get absolute mean and absolute max. Okay, so I hope I demonstrated effectively this part here. Okay, because I tell you, too many students get this wrong already. Because it's a typical trick for testing of this extreme value theorem here. Questions? Looks good. So we're going to continue. So we are done with this, which means that next Wednesday you will submit your homework for week 11. So let's continue to the last week's material, which is on mean value theorem and optimization. So right here, we're going to look at the mean value theorem. By the way, we have been like looking at theorems, right? So we started off with the intermediate value theorem, I suppose. Okay, then after that, we look at the extreme value theorem, and then now we come to this mean value theorem, right? So, well, the thing about theorems here is that they, first of all, let me get back my chat box here. So first of all, your theorems here, as you have seen, for the IVT and the EVT, right? They are pretty much quite, how to say, logical. I hope you find them logical. Okay, so sometimes theorems, right, they sound complicated, right? But it's just that sometimes if you understand the mathematics or sometimes just look at the graphical so-called representation, right, you'll find them very logical. Okay, and we use these theorems to prove many other results of mathematics. Okay, as you'll see later on, we use the MVT here, right, to actually prove the so-called monotonicity of a function, okay, which is actually referring to how a function is increasing or decreasing, okay? So the takeaway here is, after looking at quite a few theorems here already, right, is that you try to not memorize and also not be afraid of all these mathematical theorems, because sometimes, you know, they are really, you know, written in such a way that they sound very complicated, okay, and they sound very daunting. So that's what actually makes a lot of students, right, scared and dislike mathematics, okay? So therefore, from my experience is that sometimes the theorem, right, sounds very, how to say, very high level because it's filled with mathematical jargons that one wouldn't understand, a layman wouldn't understand. But you just convert that theorem, that sentence, into a graphical or visual representation, right? Most of the time you will find that it is actually very simple. It is very logical. So sometimes I just say that it's common sense, okay? Because, I mean, that's how I really feel about it. So therefore, do not be too afraid or do not be too so-called, you know, disgusted by all these theorems, okay? Really, they are just stating something that is very intuitive. And mathematics, if you go down to the so-called very fundamentals, right, many of the mathematical theorems are intuitive. Okay, the axioms, right, the truth of mathematics, they are all intuitive. Okay, so therefore, I'm going to look at this really last theorem for this course, okay, known as the mean value theorem, which I think is also something like common sense, okay, but I'm just going to demonstrate to you. So the mean value theorem is actually one of the most important theorem in calculus, okay, and we're going to look at a special case of the mean value theorem called Rolle's theorem here, right? So let's look at Rolle's theorem first because maybe it's easier to understand. And this is really, and this, I don't know, this mathematician called Rolle, right? I feel that he just kind of like steal kind of like a special case or this idea from Newton, right? If I did not remember wrongly, it's actually Newton who came up with this mean value theorem. I think Rolle's actually just, you know, kind of like steal his idea, all right, and say that, oh, this is my theorem. Okay, but it's actually part of the mean value theorem. So let's look at this first. So let's say you have a function that is continuous in the closed interval, and it is differentiable in the open interval. Okay, so then some of the students may be confused with this. How come you need f to be continuous in closed interval, but f to be differentiable in the open interval? Okay, now it's because, right, it's because of limit values. So let's say I have a function that looks something like that. Let's say I have a function that looks like that. Okay, maybe something like that. So actually, Rolle's say that, right? Okay, let us look at the so-called broad concept of Rolle's theorem first. Then I discuss about the conditions. So it just basically say that, well, if you have a closed interval A to B, then there must be a critical number such that, right, f prime equals to 0. As you can see from here, actually shows here that this is the point C, whereby the f prime is equivalent to 0. So the gradient at point C is actually equivalent to 0. as long as you have f of A equals to f of B. Okay, f of A equals to f of B. So isn't this just comparing secant line and tangent line? So if you look at f of A equivalent to f of B, and your function f is both continuous and smooth. Continuous and smooth. So this differentiable means smooth. This differentiable. Another way to say differentiable, right, is smooth. Okay, quite clearly, if the function is not smooth, it's a king, right? Then it's not possible to draw a tangent, okay, at a king. So therefore, for smooth function, you can always draw a tangent, right? So what does that mean? If you can always draw a tangent, it is differentiable. Okay, of course, as long as the tangent is not vertical. So now, if your f is continuous and smooth, right, and you have the condition such that fa equals to fb, then you must have a maximum or a minimum point. Or rather, you must have a local maximum or a local minimum, okay, whereby, of course, the f prime is equivalent to 0. Isn't this common sense? Okay, because what's the reason here? The reason here is that if you have fa equals to fb, right, then the gradient of the secant line must be 0. The gradient of the secant line, right, connecting A to B must be 0. Okay, and because this f is actually smooth, so hence you can definitely find somewhere whereby your tangent slope must be equivalent to your secant slope. That's the whole idea. Okay, and you cannot violate this no matter how you draw. Let me draw a different f. So let's say my f looks something like that. Can I violate this Rolle's theorem? I can't, because as long as my fa equals to fb, I can practically find, in this case, 3 points. 3 points of C, whereby the gradient is equivalent to 0. You see that? Okay, so there is a number, right? So I would like to maybe just change this a bit. There is at least one number C, because it is possible that you get more than one number C. Okay, there is at least one number C in AB such that you get the tangent equivalent to 0. Okay, or the tangent gradient equivalent to 0. So that's Rolle's theorem. Okay, I think maybe this is not as intuitive or as commonsensical as the intermediate value theorem and the extreme value theorem, but I think it's good enough. Okay, it's intuitive enough, right? Because no matter how you draw, you cannot violate this unless you go and draw a non-differentiable function in AB. Okay, so of course this cannot use MVT. So let me just put some cases whereby you can't use MVT. Okay, so this cannot use MVT, and also it is discontinuous. We say smooth but discontinuous, maybe like that. Okay, then you cannot use MVT also. Okay, so these cases cannot apply MVT. Okay, if your f is not smooth or not differentiable at some point inside the interval, or you have discontinuity. Okay, because we can clearly violate this, right? We can clearly violate the Rolle's theorem, right? If you have non-smoothness and you have a discontinuity. Okay, so this is Rolle's theorem. Questions before we move on? So what happens here is that we can actually use the Rolle's theorem, right, to define whether do we actually have a maximum or minimum in that interval, okay, for a particular function. So this is actually used to prove, quite commonly used to prove the existence. Rolle's theorem, right, is quite commonly used to prove the existence, right, of the critical point, okay, of a stationary point effect. Looks good. Continue. Okay, so this is the basic idea as I've shown you already, right? So there must be some horizontal tangent line somewhere in this interval, okay, if your FA equals to FB. So let's look at this example, right? To demonstrate the use of Rolle's theorem, which I mentioned that is basically to show the existence of the so-called stationary point. So if you have f equals to this quadratic function here, we're supposed to show that the function meets the criteria for Rolle's theorem on the interval 3, 7. Then I'm supposed to find the interval, or sorry, find the point, right, for which you have your stationary point. Okay, so we have to verify the three conditions. Okay, oh, by the way, I forgot. Just now I want to discuss about this interval thing. Okay, so I think continuous in the closed interval, I think this is quite clear. Okay, the interval must be closed. The interval must be closed. Then this is differentiable on the open interval. So differentiable on the open interval, right, means that in this inside AB, not including AB, inside AB, you must have f being differentiable, which means f prime must exist. So if you look at this condition here, this part, right, actually says that f prime must exist in all, or rather everywhere inside AB. Okay, then some of you may ask, why not change this to this thing? Does it make the difference? Does it make a difference? Well, it does, because strictly speaking, f prime actually does not exist at the endpoints. You think about that. Okay, because at the end, right, we are not able to prove the so-called left-hand limit equals to the right-hand limit. It's not possible. Okay, at this left limit, right, it's not possible to prove that there is a left-hand limit because there is no left-hand limit already, right? Because you're right at the leftmost point. Okay, so therefore this f prime must exist because this f is differentiable, right? So this interval must be open, okay, using the round brackets, okay, using round brackets. So therefore this is actually a strict mathematical condition. So hence, this is why you have one is closed interval and the other one for smoothness is actually open interval. Okay, I hope that makes sense now. So coming back to this example, so we have the quadratic function, and then we have to verify these three hypotheses. So continuity must verify first. So of course, this is just quadratic function, it's a polynomial, right? So continuous in all R. Differentiability. So of course, when we differentiate this guy, right, it's going to be just giving us a linear function, okay, 2x minus something, for example, 2x minus 10. So therefore, the f prime exists everywhere also, okay, f prime exists everywhere also. So therefore, exists everywhere means, right, in the interval also exists, okay, obviously. So then subsequently, we have to check whether other endpoints equal. So we check f3, which is the left limit, and f7, which is the right limit, and we realize that the function values are the same. Okay, so which means the three conditions are met. Three conditions are met. So therefore, we can say by Rolle's theorem. So once three conditions are met, let me just write a tick here. So then we can say by Rolle's theorem, there exists some or at least one C. At least one C such that f prime C equals to 0. Okay, then we can proceed on to find that C already. So therefore, set your f prime equals to 0, realize that x equals to 5, and then subsequently realize that 5 is inside 3, 7. Okay, so practically it's just a double check. Once you satisfy Rolle's theorem, right, this number, your critical number, will definitely be inside 3, 7 already. Okay, so let me just put a note here. Will definitely be in 3, 7. Okay, when Rolle's theorem is satisfied. Okay, questions? So by the way, if you happen to solve for this critical number that is outside the interval, and yet you met the 3 hypotheses, right? Which means that your calculation got some problem. So that can be used to serve as a check for your critical point as well. Okay, so you must make sure that that critical number is inside your interval. Looks good. So I'm going to jump into MVT now. Okay, so just now I mentioned that Rose is like a thief, right? That stole who stole this idea from Newton's. Okay, so let me show you what is actually the mean value theorem. It is actually so-called a broader theorem that includes the Rose theorem as well already. Okay, so the mean value theorem says that. Okay, let me just use this graph to demonstrate. So as long as your f is continuous and smooth, okay. So in this case, right, you do not need the condition fa equals to fb. Okay, you do not need this condition fa equals to fb. They can be different values. Now, the mean value theorem says that if your f is continuous and smooth in this closed interval, then there must be some point C, or there must be at least one point C in AB, such that the gradient of the tangent is equivalent to the gradient of the secant. You see that? Okay, so no matter how you draw this smooth curve, you must make sure that your curve is smooth. You are always able to find some point where you can draw the tangent line that is parallel to the secant line. That's the idea of the MVT. Okay, so of course, you can always just draw such that FA equals to FB. Now, when you draw FA equals to FB, then there must be some point C whereby the tangent is horizontal. So that's actually the Rose theorem. So you see that? Okay, so MVT actually is a broader, right? It's a broader theorem that encompasses Rose theorem already. Okay, so in order to be true, right, the function has to be continuous and differentiable on the interval. Okay, that's that's two very important conditions. Okay, so this is the whole idea of MVT here. Okay, so this is what it is. And what is this? This is actually the gradient of the secant line. Okay, so gradient of tangent line must be equivalent to gradient of secant line. Okay, there is actually at least one number C that can satisfy this equation. So this guy is your gradient of tangent line. Okay, right, so that's what it is. So therefore, if you look at this point 2 here, right, it's just a rearrangement of this f prime c, okay, multiplied by b minus a, multiplied by the interval, okay, is equivalent to fb minus fa. Okay, so actually you might observe that actually this is just your linearization. fb is equals to fa plus f prime c, right, multiplied by b minus a. Okay, just a linearization, and it is because we are looking at the tangent line. Okay, so the consequence of this statement is actually saying that if your gradient is positive, then your function value must increase in that interval. I repeat again, if your gradient is positive, that means your function value must increase. Okay, because b minus a is always positive, because we always treat b is on the right side of a. Okay, b is more than a. So therefore, this guy is always positive. Then if this guy is positive, FB minus FA got no choice, got to be positive here. Okay, so by the mean value theorem, right, we can actually decide on the so-called increasing or decreasing characteristic of a function. Okay, so if f prime is positive, then f must be increasing. So there's a consequence here. So the consequence is if f prime C or f prime is positive, then f must increase. Okay, and vice versa. I just write and vice versa. Okay, so you can see this is actually a result of the mean value theorem here. So the relationship to Rolle's theorem. So this is actually, both of these are MVT. Okay, but this is Rolle's. All right, okay, so that's why I say MVT is a broader theorem that encompasses Rolle already. So let's take a look at this example. We have this cubic function, right, whereby we have a equals to 0 and b equals to 2. So the interval is actually 0, 2. So now we ask, what is the value of x that satisfies the MVT? Okay, so satisfy the MVT means, right, the gradient of the secant line must be equivalent to the gradient of the tangent line. But before that, you have to make sure you check, okay, the conditions. So f is a polynomial, so therefore continuous and differentiable in R. So two conditions satisfied. So hence, right, we find the slope of the secant line here. So the slope of the secant line is just f2 minus f0 divided by the interval 2 minus 0. Okay, so we get 6 minus 0 over 2, we get 3. So hence we are asking, right, where is the point C such that the gradient of the slope is actually equivalent to 3? Okay, so hence we find f prime. So we get 3x squared minus 1. Equate this to 3. Equate this to 3. Okay, because you want to find where is the point x such that the two gradients are parallel. Okay, then subsequently you get x equals to 2 over square root 3 and minus 2 over square root 3. Now you have to make sure that this is inside 0, 2, as I have mentioned just now. Okay, so is this a valid value? Yes, it is, but it's not inside the interval. It is not inside the interval. Okay, so if I eyeball this, right, you can pretty much agree that, right, this point, I think about, let's say about this point, there is also another point whereby you get the tangent line being parallel to the secant blue line. Okay, so this point is also a valid point, but it's outside this interval. Okay, so therefore you cannot apply the MVT. So hence we found that C equals to this number here, and then we just decide that that is actually our critical point. Okay, so that is our stationary point or stationary number that satisfies the MVT. Questions? Okay, good. So you can see actually the similarity between applying Rolle's theorem and applying MVT is pretty much identical. Okay, it's just that for Rolle's theorem, right, you will get your f prime equivalent to 0. Okay, set your f prime equivalent to 0 and then find that point C. Whereas in the mean value theorem, set your f prime equal to the gradient of the secant line. Okay, so this is actually just a fundamental difference between the two theorems here. Okay, applying the two theorems here. So let's look at this example first before maybe we can go for a break. So explain why the MVT does not apply for functions over the given interval -1 and 1. Okay, so you can see this guy, right? Modulus of x minus half. So modulus of x minus half, if you just want to do a quick sketch, we know that this is minus half. And modulus of x brought down by minus half. So this is my mod x. Okay, so this is my f of x. So clearly you can see that this is not differentiable, but more importantly, the not differentiable point is actually inside -1 to 1. Okay, so this is inside -1 to 1. So hence, right, let me just put a note here. Not differentiable at x equals to 0. At x equals to 0, which is in -1 to 1. Okay, if the not differentiable point is outside -1 to 1, then you can apply the MVT. Okay, let me put a note here. If this point is non-smooth point, if non-smooth point is outside interval, then MVT can be applied. Understand that? Okay, so it's not necessary once you see this kind of function, right, that is not differentiable at some point, you straight away tell me that this MVT cannot be applied. Okay, which is not true, right? Because not differentiable, that point must be inside the interval. Then you cannot apply MVT in that interval. Okay, so I hope that is clear. Then next, what about this guy? So this guy is not continuous, just 1 over x squared, right? So 1 over x squared is clearly looking something like that. So this is my 1 over x squared. Okay, so 1 over x squared, as you can see here, right? Not continuous at x equals to 0. That is also inside minus 1 to 1. What about if I change my interval to 1, 2? Can you apply the MVT to 1 over x squared? I repeat again. If I change this interval to 1, 2, can you apply the MVT to this function 1 over x squared to find some point C? The answer is yes, because x equals to 0 is not inside 1, 2. It is not inside 1, 2. So where is 1, 2? 1, 2 is here. So isn't this completely smooth here? Completely smooth and completely continuous. So you can apply MVT to 1 over x squared inside 1, 2, not across x equals to 0. All right? Okay, so get this idea, all right? The interval where the non-differentiability and the non-continuity appears, it must be inside the interval. Then it violates the use of the MVT. Okay, so lastly, let's look at this guy. Function is discontinuous at x equals to minus 1 quarter, 1 quarter. Okay, which is quite clear because, hold on, let me just increase the size here a bit. Okay, so for this tangent 2 pi x, right, actually you can rewrite this into sine 2 pi x over cosine 2 pi x. So clearly we can observe that this guy is actually undefined, right, or discontinuous. Okay, discontinuous at points whereby cosine 2 pi x is actually equivalent to 0. Cosine 2 pi x equivalent to 0. So therefore, right, what is your 2 pi x? What is your angle? So 2 pi x must be equivalent to what? Pi over 2, right? Because cosine pi over 2 is 0, right? Okay, cosine pi over 2 is 0. Or rather, to make it more general, plus minus pi over 2. Okay, because you rotate clockwise or you rotate counterclockwise, right? 90 degrees will give you cosine equivalent to 0. Okay, then quite clearly you can observe that plus minus 3 pi over 2 is also giving you 0. Then plus minus 5 pi over 2 and so on and so forth. It's also giving you 0. Okay, so dot dot dot. So hence, right, if 2 pi x equals to plus minus pi over 2, plus minus 3 pi over 2 and so on and so forth, divide by 2 pi throughout, you get x equivalent to plus minus 1 quarter, plus minus 3 quarter, plus minus 5 quarter, and so on and so forth. Okay, so now you check. So you got multiple discontinuity points. Okay, multiple discontinuity points. In fact, infinite of them, right? Because this is a purely, periodic function. So therefore, right, check at which of the points of discontinuity is inside this interval. So you realize that actually, right, you have actually, let me see, minus 1 to 1. Oh, actually you got 4 points. You got 4 points of discontinuity. So let me put a note here. This part. Okay, 4 points of discontinuity inside -1, 1. Observe that. Okay, so 4 points of discontinuity. So clearly you cannot apply MVT over this -1 to 1, right? For the tangent to pi x. Questions on the 3 examples? Okay, so let me also say this, this one, make it more complete. Okay, so you can of course verify this yourself, right? Tangent 2 pi x, you can just quickly plot it out. Okay, so you can see that -1 to 1, right? How many asymptotes you have? How many vertical asymptotes you have? 1, 2, 3, 4. Okay, -1 to 1, right? 4 asymptotes. So 4 discontinuity points. Okay, so I hope this is a clear enough demonstration, right? That the continuity as well as the differentiability conditions are critical, okay? In order for you to apply the mean value theorem. So this is actually one more requirement as compared to the IVT and the EVT, which just requires the continuity of your function. Okay, whereas the MVT requires not only the continuity but also the smoothness of your function. Okay, in a specified interval. So I hope this is clear, and let's take a break. So we have a break for maybe 6 minutes, and that will be till 12:20. So let us continue. So as I've discussed just now, we can actually use the mean value theorem to prove the increasing or decreasing characteristic of the function. Okay, so therefore I mentioned that if your f prime is positive, then function must be increasing. If your f prime is negative, then the function must be decreasing. Okay, the derivative is 0, then the function is constant. Okay, because fb minus fa is in fact 0 in that case. Okay, so if the two functions have the same derivative, then the two functions differ only by a constant. So actually what this is trying to say is quite clearly, if you have f of x, okay, let me give an example. So if you have f prime of x is equivalent to, let's say, 2x. So what can f be? It's possible f of x is equivalent to 2, or rather x squared. Okay, so if you differentiate x squared, get 2x, right? It's very clear. But however, is that the only choice? Not really, right? Because it is possible that if I have another function g prime x is also giving me 2x. However, my g of x could be x squared plus c, constant. Okay, so clearly when I differentiate x squared plus c, you still get 2x. So therefore, what is this? You can see that the two functions, right, differ by a constant. Okay, differ by a constant. Okay. So this is a demonstration here. So how does this relate to the IVT? Now, we can say this, right? If let's say your function is x squared, okay, so let me just draw. So let's say if my x squared, maybe looking something like that. Okay, then my g of x, okay, let me draw this lower. So this is my f of x. And then my g of x is just differing by a constant c. Okay, so where's the c? The c is here. So everywhere differs by c, right? Because g of x just plus c, okay? Let's say c is positive, so therefore g of x is above f of x, okay? So therefore you can see that by the intermediate value theorem by the mean value theorem, this fb minus fa is equivalent to f prime sum c multiplied by b minus a. Okay, so because your f prime and g prime is actually the same, so g of b minus g of a is equivalent to g prime c multiplied by b minus a. Okay, because your f prime and g prime, they are exactly the same. You see that? Okay, and then b minus a also exactly the same. Let's say we talk about the same intervals. So this is a, this is b. Okay, so we can observe that if the right hand side for the two equations are equivalent, then the left-hand side must be equivalent as well. You see that? They must be equivalent as well. So therefore, this point minus this point must be exactly equivalent to this point minus this point. So what does that mean? They must only be different by some constant c. Is that all right? Okay, so that's the whole idea there of using MVT to show that the functions are just differing by some constant c if they have the same f prime values. So key concepts, you can go through this yourself. And we're going to move on to looking at concavity now. Okay, so previously we talked about derivatives, and then we said that equals to 0. We know that when the gradient or the slope is equivalent to 0, you get some stationary point, maybe representing a maximum, minimum, or a point of inflection. Okay, now we are going to talk about the shape of the graph. Okay, so this shape of the graph, right, is determined by this concept called concavity. Concavity, yeah. Okay, so I'm going to discuss what is concavity. And this concept of concavity will allow us to so-called classify, okay, whether our stationary points are maximum, minimum, or inflection points, or in fact other points as well. Okay, so how derivatives affect the shape of the graph? What does f prime and f prime prime say about f? Okay, so this is actually the question or the layman statement that we are answering here. So if you look at some very so-called fundamental understanding, so you can see here that if your f prime is positive, that means your f of x2 must be more than f of x1. Okay, for x2 more than x1, right? So for example, x2 is somewhere, some point here, and x1 is some point here. Then we can say that if your f prime is positive, as you can see, all right, f prime is positive all the way here, okay, and therefore f at x2 must be more than f at x1. Okay, so of course a result of the MVT as we have discussed. Okay, left hand side must be equivalent to right hand side. So the same goes with decreasing. Okay, so it's quite intuitive. Then now, so this is increasing again, so this is positive again. Okay, so therefore negative means decreasing, positive means increasing. Okay, simple as that. So the increasing or decreasing test, right, is also known as the first derivative test. Okay, because this is a first derivative. So therefore, let me just write here, first derivative test. Okay, so if f prime is more than 0, then f must be increasing in the interval. If f prime is less than 0, then f is decreasing on the interval. Okay, so we have already proven using the MVT, right, to show that already. Okay, f prime x minus some fixed point a, then that is equivalent to f at x minus f at a. Okay, can clearly see that, right? If this is positive and x is always on the right side of a, right, for x, for some x that is more than some left limit a. Okay, so this point must also be positive. Then this guy must be positive already. Okay, so if this is positive, then there can only be one result. Fx must be more than equal to Fa. In fact, it's strictly more than Fa. Okay, so mean value theorem in action. So let's take a look at this example. So find where the function, this quartic polynomial, right, is increasing and where it is decreasing. So first of all, we find those points whereby f prime equals to 0 first. Okay, because we know these are the turning points. So when the graph turns, right, there is a change in the increasing or decreasing characteristic. Okay, so these are the turning points. So find those turning points first. Then subsequently, we categorize the interval according to f prime equivalent to 0. Okay, so because you can get multiple turning points. So therefore, between each turning point, let me give you an example here. So let's say you have one turning point here, another turning point here. Okay, so how do we know this is turning point? Because we know that the f prime is equivalent to 0. Okay, f prime equal to 0. So once you get these two turning points, right, you can actually see that there are intervals now. So this is an interval, this is a limit, this is also another limit. So this is one interval. Let me have more space here. So you classify or categorize your intervals. Okay, so let's say this is actually A, B. So maybe inside AB, you have to check. Okay, you have to check. Then before A, you have to check. After B, you have to check. Okay, so therefore you got 3 intervals to check your f prime. Okay, your f prime. See that? All right, so evaluate f and f prime, right, in each of the interval. Okay, so that's what I'm trying to say here. So hence, let's look at this guy. So first of all, we solve for f prime equals to 0. Okay, so when we solve for f prime equals to 0, right, actually you get a cubic equation. Let me see if they will have the answer here. So differentiate, you get a cubic equation, and then you factorize. Okay, of course, this can be done quite easily using your calculator. Right, so of course it's open book, so you don't have to worry too much about this factorization of cubic expression. You can just solve using a calculator directly the roots. Okay, so therefore you set this f prime equals to 0. Obviously you get x equals to 0, x equals to 2, and x equals to -1. So you have your critical numbers or your stationary numbers. Okay, because you set f prime equals to 0, right? So all these are actually potential candidates for stationary points. Okay, so then you divide into 4 intervals. As you can see, 0, 2, and -1. So how many intervals are there? 1, 2, 3, 4. Okay, so before -1, -1 to 0, 0 to -2, and after 2. Okay, so 4 intervals. Then you check what are the f prime values. Okay, so f prime values, substitute in slightly before x equals to -1. Okay, so in this case, right, you do not really need to go and press calculator, because if you were to press calculator for each of the cells here, right, you're going to waste a lot of time. What we do is we simply just check the polarity. Okay, because remember, we are just looking at whether f prime is positive or negative to decide whether your function is increasing or decreasing. We are not looking at what is the absolute value of your f prime. Okay, so we just check polarity, and it's very simple in this case. So once you have this so-called factored form of your polynomial, what you can observe is if you have this part, you realize that this is a negative number. So hence, right, you can observe that in this interval. Okay, let me just find some space to do it here. Hold on. Okay, let me just do a demonstration here. So this is your function, or your f prime. So you have 12x, x minus 2, x plus 1. So how to check the polarity? Now notice that this f prime x, right, at x is equivalent to -1 minus, slightly to the left of -1, slightly to the left of -1. Or you can consider -1 to minus infinity as well. Okay, so on the left of -1, okay, let me just put this more generally, x less than -1. So if this is -1, right, obviously this first term is going to give me a negative value. Okay, first term is negative. What about the second term? Now, if this is -1, this is -1, -2, of course, this is going to be negative. There's no choice. Okay, because it's negative, negative, right? So minus, minus, so minus overall. What about this? Now, you can see that when this is -2, for example, -2 plus 1, this guy is going to be negative as well. So minus, 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 that's how you get this 3 minus here. You see that? Okay, so minus, minus, minus equals to a negative number. Is that all right? So just one demonstration for one column. Is that okay? Can, So what about -1 to 0? So maybe let's do another one. -1 to 0. So for -1 to 0, you can observe that this guy is going to be still negative. Then this guy is going to be what? So this is actually negative, negative, minus, minus again. So therefore, this is also going to be negative. What about this guy? But this is between -1 and 0, right? Between -1 and 0. So you can consider me something like -half. So if you have -half here, then this is a plus. So this guy got to be positive. So minus, minus, positive, the net result is positive. You see that? Okay, so I'm just trying to give you another demonstration here. Right? So you can repeat the same for 0 to 2 and 2 to infinity. Yeah? Okay, so I believe I don't need to go through these two columns anymore. And once you get the polarity of f prime, you know the shape of your graph already. You know the shape of your graph already. Okay, so at this juncture, actually, what you can do, right, in order for you to sketch the graph is this. Okay, because once you go from negative to positive, at this point, right, you intuitively know that this is a minimum. Okay, which means that at this x equals to -1. Sorry, at x equals to -1. Okay, let me draw the graph. It's not very clear here. So which means I can actually do this. Okay. So I do not know the function value, okay, but I can of course find out. It's not too difficult. So hold on. Okay, they didn't find me the function values. Okay, function value not important, right? But what's important is this is a -1. Then I know that there is some point. Okay, let's say this is the function value at 1. Okay, of course, this may not be correct, but doesn't matter. So let's say this is the function value at -1. So I can get this function value. Then subsequently, because I already know from my first derivative test, right, that this guy is negative sloping gradient. Hold on, let me use the same color. Negative sloping gradient. This guy is positive sloping gradient. So which means I'm able to sketch this point already. So there is a minimum point here. Okay, there's a minimum point here. So hence, I can repeat the same for the other 2 points. So at x equals to 0, maybe my f at 0 is there. F at 0. Okay, so this is f at 0, and I realize that you have increasing, decreasing. So hence, I can sketch this point. I know it's going to look something like that. Okay, and so on and so forth. So therefore, with that, right, I can actually start to link up my graph. Okay, so I can actually start to link up my graph after I know all this information. Okay, maybe something like that. All right, so of course, there's another minimum point here, but I think you get the idea. Okay. Questions on using the first derivative test, which is one of the 2 types of tests we can use to classify the type of stationary point that we have. Okay, so practically there are 2 types of tests whether you can use, right, to check whether you have a mean or max. One is the first derivative test, as we saw here. The other one is the second derivative test, which is your f prime prime test. Okay, then many students actually will ask, right, when to use which. So it depends. If your function or if your f prime function can be factorized out easily, such that you can get the polarity check done easily, then the f prime will be advantageous. Okay, I repeat again. If you can factorize this expression for your f prime in this form or maybe in a fractional form, such that you can evaluate the polarity of each term easily, like in this example, then the f prime check will be efficient. Okay. However, if you can't do that, then maybe you want to consider the second derivative test. Okay, so the drawback of the second derivative test is that you have to differentiate one more time. And some functions can be horrendously difficult to differentiate another time. Okay, so therefore it's very tedious. So when the function is too tedious to differentiate, right, we will fall back or we will try to use our first derivative test. Okay, but even that may not be so easy. Okay, I must say this first, right? Because if let's say you cannot factorize out in this form, you have this form, do you think it is that easy to actually analyze the polarity? It's not, right? Because you actually have to key in some sample values into your calculator and calculate what is the exact value. Okay, so hence, right, there are pros and cons of each method, and I must say that sometimes both methods are tedious. Okay, so let's move on. Okay, so basically this is what we have done now, right? Use the first derivative test to check the sign of f, right, in the vicinity of each critical point to decide whether you have a maximum or minimum or stationary point. Okay, so you can see this example here, right, whereby we have f prime a is undefined. So we need to check to the left as well as to the right of f prime a. So we observe that in this case, right, our f prime is positive on the left, f prime is negative on the right. So hence, this must be a local maximum. Okay, it's one of our critical points, which is non-stationary. Then there's another one, local minimum here, right? And then you check that actually the gradient here is actually negative and the gradient here is actually positive. Okay, so therefore a local minimum, right? Because it goes from negative to positive gradient. Okay, just imagine how the slope changes. So as you can see, when you have point C, you realize that before the slope or before the critical point, right, or before the stationary point, you have positive slope. But after the critical point, you also have positive slope. So when you have no change in polarity of the slope, can be positive to positive or negative to negative, right? You have this inflection point, okay, a point of inflection, right? So then, of course, point here maximum because it goes from positive to negative. Okay, so this is actually negative to positive. All right. So let's use this example. We have to use the first derivative test to locate all the local extrema for this root expression here. So the first step is to find the derivative, set it equals to 0 and do not exist to find all the critical points. And then to classify each critical point, we apply the derivative check in the vicinity of each critical point. Okay, so that's what we'll do. So step 1, find the derivative, right? So you just differentiate accordingly. And then if you inspect this process, right, actually, this is actually your f prime already. Okay, so really the use of this simplification process to make it a common denominator is really to put it in a form such that you can use your first derivative test easily. Okay, I repeat that again, right? But I know, let's say there are some expressions that doesn't lend themselves, right, to this manipulation. Okay, you can still apply the second derivative test directly on this expression. Okay, as I will demonstrate in a while. All right, so let's use this expression to apply our first derivative test here. So now set this equal to 0 or undefined, and you can expect that when x equals to 0, right, this is going to be 5. Okay, because 1 minus 0 here, 0 to the power of anything, right? 4/3 here is actually 0, so you get 5. So when x equals to 0 here, this is 5 over 0. So which means x equals to 0 is actually a critical point. Okay, x equals to 0 is actually a critical point. Subsequently, you set this f prime equal to 0. So you multiply by the denominator throughout, you get only the numerator equivalent to 0. Okay, of course, you get 5 times this guy equivalent to 0. Then you divide by 5 throughout, right? You still get this expression. All right. Then subsequently, you bring the 1 across and you get x to the power of 4 equals to 1. So why is this so? So quite obviously, this is x to the power of 4/3 equals to 1. Okay. So if you have x to the power of 4/3 equals to 1, this is cube root, right? So this is really just x to the power of 4 cube root equals to 1. So then you cube both sides. So when you cube both sides, you get x to the power of 4 equals to 1. Is that right? Okay. So actually, there are actually 4 roots here. 2 of them are imaginary or complex roots. So 2 of them are real roots. Okay. So therefore, we just consider real numbers here. So hence, you get x equals to plus minus 1. So quite clearly, if you have plus 1 to the power of 4, you get 1. Minus 1 to the power of 4, you still get 1. Okay. So hence, your 2 real roots are plus minus 1. So hence, altogether, right, you actually have 3 critical points. Okay. 1 at 0 and the other 2 stationary points at minus plus 1. Is that right? Okay. So after you found your 3 critical points, right, you do not know what type of points they are. So now we need to classify the extrema. What are the type of extrema that we are looking at? So then we apply our first derivative test to the vicinity of 0, 1, and minus 1. Okay? So that's what we do, right? And this is the part whereby I mentioned that this form comes in handy here. Okay, because it allows us to find the polarity very easily. Of course, this 5 is irrelevant because this is just a positive number. So hence, if you look at this 1 minus 4 x to the power of 4/3 divided by this 3x to the power of 2/3, right? So split up your intervals. So you have you have minus 1, 0, and 1. Those are your critical points. So then, first interval, minus infinity to minus 1, we check. So look at this guy. So if, let's say, I'm looking at x less than minus 1, so what's going to happen? X less than minus 1. So you can see that if x is less than -1, right? So we have -1 to the power of 1/3 is still -1. But after that, you raise it to the power of 4. So therefore, this guy is going to be a positive number. Okay, it's going to be a positive number. So what is this? This is going to be a negative number because this guy is going to be more than 1. Okay, let me repeat again. Let me repeat again. So sometimes you need to analyze step by step. So at x equals to, as x is less than -1, x to the power of 1/3 is actually still a negative number. This is a negative number, okay? But x to the power of 1/3 to the power of 4 is now a positive number. Is that all right? Okay, right? So therefore, this guy, right, is actually a negative number because, right, this is x to the power of 4, right? This is x to the power of 4. So you must imagine when this is less than -1, the absolute value here, right, is like, for example, -2. So if you think about -2, right, you raise it to the power of 4, you're going to get a positive value that is more than 1. That is more than 1. Okay, so therefore, if you take 1 minus something that is more than 1, you get a negative number. Is that right? Okay, so hence 1 minus this thing is actually a negative number. Okay, since this part, right, is actually the absolute value of this is actually more than 1. Okay, it's positive and it's more than 1. All right. So if this is too, fuzzy for you, it's okay. Just substitute in some convenient values and you can press your calculator. Okay. Of course, we are trying to cut down the amount of times you press calculator here. Okay. That's the purpose of this polarity test. Subsequently, x to the power of 2/3, which is the denominator. So this is power 2/3, but this is actually just x to the 1/3 square. X to the 1/3 square. So therefore, if this is a negative value, you get 1/3 still being negative, but however, you square it, so it becomes positive. So hence, you get x to the power of 2/3 being positive. Is that right? Okay, so hence, negative divide by positive, you get negative. Okay, so that demonstrates the first column. Okay, so hence, let me just write down here. This guy is actually negative. This guy is actually positive. So this is only for x less than -1. This is actually negative, and this is actually positive. So divide negative by positive, you get negative here. Questions? So you just repeat the same approach, right, for the other two intervals. Okay, so quite clearly, you can see that this is a decimal number, right? 0 to -1, right? Between 0 and -1, this is a decimal number. Okay, this is a negative decimal number. So therefore, if you look at this expression, now you take a decimal number, you cube root it, you still decimal. However, you trace it to the power of 4, you still get a decimal. So therefore, this is less than 1. This is some positive value that is less than 1. So hence, if you take 1 minus something less than 1, you get positive. All right? Okay? So therefore, if this is something that is negative, you square is always positive. So positive again. So positive divided by positive, positive. Okay? So definitely this takes some practice. Okay, it takes some practice. And so I must once again reiterate that for some expression, I can't do this so easily. Okay, I can't do this first derivative test so easily, right? So maybe we want to consider the second derivative test if your function is not so nice, not so nicely put in the factored form. Okay, so therefore, for the other two columns here, right, I'll leave you to check, right? So hence we have a minimum point at -1, and then subsequently a maximum point at 1, and then what about at 0? So at 0, right, you realize that the f prime polarity does not change. Okay, so positive to positive, right? So hence we get a point of inflection. Is that all right? So the whole idea here behind the first derivative test, right, is to classify what kind of critical points you have over the specific interval. Okay. Right. So you can see that this is indeed a point of inflection here. Okay. So we have a minimum at -1, maximum at 1, and then this is a point of inflection. Okay. So this is why you have do not exist, f prime do not exist here, right? Because your gradient is actually infinity. Okay. But nevertheless, before and after, right, the gradient is actually positive. So that's of course in agreement with our analysis, our first derivative test just now. I'm left with 9. Whether you guys are still able to take it. I can actually start on concavity. Let me see if I want to. Okay, I think I'm going to stop here because concavity is actually quite a big chunk, which actually leads on to the second derivative test. So I'm going to stop here a bit early. Do you guys have any questions? Because I don't know, like for the subsequent lessons, recently I don't get that many questions. So I'm not sure if you are lost or if you are finding this too easy. All good? Is there any doubts that you want to clear? Anyone? I hope I'm not talking to myself. Yeah, I need time to absorb. Okay. Okay, so in any case, right, you can just Teams me your questions. Okay, maybe make a drawing. If you find it difficult to describe using your words, okay, make a drawing and then just take a photo and then upload to our Teams channel, right? And then you can ask me questions, or you can, what do you call that? Message me privately as well. Okay, so we are done today, and then next, I suspect I should be able to finish everything by this Friday. Okay, so therefore, this Friday we close the entire 12 weeks of material. Then next week, our week 13, we are going to have revision. So I suppose after this Friday, right, I will post some of the past year papers, past year final exam papers. Then you guys go and try it out. And then maybe Wednesday and Friday we can go through. All right. So you can also prepare your questions to ask because pretty much after our last lesson next Friday, the following week is your exam ready. Okay. So if you have no questions, then I will call it a day. All right. That's good. Thank you very much for your attention. That's all. Thank you.